Good afternoon. Today we will start learning about series that may have negative terms. If you review the previous lectures that we talked about in terms of convergence of series, you will notice that all of these convergence tests we learn concern only series with positive terms, with the exception of the first one. Remember the divergence test. So just to review this, the divergence test which simply states that if you have an infinite series, if an, the sequence that forms the series, doesn't go to zero, then in the limit, then the series is divergent. And that's all it says. Remember, there's nothing else to be said from this test. There's no way to figure out the convergence on using this test. But anyway, this concerns any series basically. So it doesn't have to be with positive terms. All the other tests we learned, the integral test, the comparison test, ratio test, and so on, all of these concern series with positive terms. Not ratio, I'm sorry, the limit comparison test. So those concern series with positive terms. So today we'll learn a type of series that may have negative terms, but not just any series with negative terms, but the one in which the negative signs alternate, as the name implies. So the formal definition of an alternating series is of the form summation from 1 to infinity minus 1 to the n minus 1 bn, where bn stands for a positive number. Okay, so the sign alternance is captured by minus 1 to the n minus 1. It doesn't really have to be with n minus 1, it could be minus 1 to the n. As long as the signs alternate, then that's an alternating series. This one, the one we're going to formally use in this section, is the one that starts with a positive number, which is the reason why you have the first exponent the exponent n minus 1, so that it's 0 when n is equal to 1, which makes it positive in the beginning. So if we expand this summation, we have minus 1 to the 1 minus 1, b1 plus minus 1 to the 2 minus 1, b2, and so on. So I hope it's clear why you put n minus 1. So you want to make the first one to be the positive one, because 1 minus 1 is 0, minus 1 to the 0 is 1. So therefore, if we expand this, this becomes b1 minus b2 plus b3 minus b4, and so on. And then again, a typical nth term will be minus 1 to the n minus 1 bn. In general, the convergence of more general series in which you may have positive or negative terms, but not necessarily alternating like this, the convergence for those types of series is a much more difficult problem. It can be a tricky business to prove convergence in that case, and it's not the object of our class. So to summarize, pretty much all the series with negative terms that you may see in this class are the alternating series that we study in this section. So let's come up with a couple of examples. One that I'm going to discuss immediately. Let's say you have summation from 1 to infinity minus 1 to the n minus 1, 1 over n. So that's going to be 1 minus 1 half plus 1/3 minus 1/4, and so on. And we're going to compare this with the p series with p equals 1, the famous series summation of 1 over n, which is 1 plus 1 half plus ... 1 over n, and so on, which, remember, you should know by this point that this is divergent, because it's a p series with p equal to 1, and a p series converges only if p is greater than 1. So in general, the summation of 1 over n to the p converges only if p is strictly greater than 1. But this is a classical example that you might remember separately from all other series. And I'm going to go back to this. I put this side by side because it's important not to confuse the two. These are two completely separate series. This is an alternating one, and this the right hand side is the one with positive terms. And again, because people often confuse things in the beginning, especially if they go back and see this bn greater than 0 and say, okay, well, don't we have negative terms? Remember, we do, but those negative terms are captured in the way we write it by this -1 to the n minus 1. So therefore, the sequence that appears in the alternating series, it's still a one with positive terms. But the series itself is made of not just bn, but -1 to the n minus 1 times bn. So without further ado, let's state the convergence test that concerns alternating series. I'm not going to prove it, I'll just illustrate briefly why the test is true. I mean, like why the convergence can be established from those conditions. So the alternating series test, which we will abbreviate from now on by AST, basically looks at three conditions for the convergence. Excuse me, the two conditions for the convergence. So if the alternating series summation from 1 to infinity -1 to the n minus 1 bn, where bn again is made of positive terms. So if this series satisfies two conditions, so the first one is bn is decreasing, so that means bn plus 1 less than or equal to bn for all n, so bn decreasing. So this is how it appears in most books, that bn should be decreasing. In reality, the decreasing doesn't have to be for all n. It can be for all n greater than a number. Remember the golden rule, not the golden rule, but the overarching rule that if you look at a series, if the first couple of terms don't fit a certain pattern or certain hypothesis that you need, that doesn't really matter if the rest of the series satisfies those conditions. So in other words, with respect to convergence, it doesn't really matter whether you're looking at the infinite sum from the beginning or from the second term or from the third term. If you still look at all infinitely many terms from that point on, and if the theorem applies in those cases, then the convergence can still be established. So in other words, subtracting or adding the first couple of terms won't change the convergence of the, whether the series is convergent or not. But for simplicity and to make things a little bit more streamlined, most books will state the condition like this, like for all n. Well, when in reality it's just for all n except maybe a couple of first ones. That'll be also good enough. So bn must be decreasing, and the second condition, the limit of bn as n goes to infinity must be equal to 0. Which, if you think about it, that's really not surprising. Because of what we actually learned from the the divergence test. So then if these two conditions are satisfied, then the series, the alternating series, is convergent. So when you are faced with an alternating series, there are two conditions to verify to conclude it is convergent. So let me illustrate actually before I show you with a couple of examples how you check this hypothesis. Let me illustrate a little bit why this is actually true. I mean, why you need these two conditions for convergence. Remember, which is true for any series, right? So if you have in general a series, an infinite series, by definition this is convergent if the limit of the partial sums, so if the limit as n goes to infinity of Sn, which is the sum of the first n terms, is convergent. This is not a criteria for convergence, that's just the definition of what we mean by convergent for a series. So the partial sums for an alternating series, if you go back to the alternating series itself. Notice that the first partial sum is b1, so you start with a positive term. The second one is b1 minus b2, the second partial sum. Then the third one is b1 minus b2 plus b3. And let's write another one all the way up to the generic one up to minus 1 to the n minus 1 bn. So I want to illustrate why it's key basically that these B, A1, B2, Bn, this sequence made of the Bn's, why it's key that it's decreasing. So suppose that you actually write down these partial sums on the x-axis. And if you look carefully, because Bn is decreasing, what you add or subtract at any given point, it's going to be less than what you added or subtracted at the previous step. So basically B1 is going to be the biggest one. It's going to be somewhere here. So B1, which is identical to S1, to the first partial sum, let's say is positioned over there on the x-axis. And then you subtract B2. But you know, B2 is less than B1. So when you subtract B2, you're not going to go all the way back to 0, but you're going to go all the way back ahead of 0, somewhere here. So this is B1 minus B2, which again, that's the second partial sum. Now, when you move to S3, you're going to add, again, a positive quantity. But that thing that you add is going to be less than what you subtracted before. Because remember, all these numbers are in decreasing order by our hypothesis. B1 is greater than B2, greater than B3, greater than B4. So when I add B3, I'm not going to go all the way back to S1. I'm going to go all the way back to some quantity less than S1. So S3 will be here. And again, you can repeat the process, right? When you move on to S3 from S3 to S4, you're going to subtract something, but you're going to subtract something less than you added before. So you're going to land somewhere ahead of S2. So S4 will be here. And then keep on going, S5 will be here, S6 will be here, and I hope you see the pattern that at some point these terms of the sequence of partial sums will approach a finite limit. So basically, if the alternating series is convergent, that limit essentially, if you start of course with the positive terms, that limit is going to be basically situated between 0 and essentially the first term, S1, which is again identical to B1. So we have room actually for a quick example, and we're going to do another one on the next page. All you have to do, it's really simple actually for most applications, for most examples. All you have to do is to recognize when you have a series with alternative terms. And if that's the case, then you need to check two conditions to see if it's convergent or not. So for example, if I go back to the series of minus 1 to the n minus 1, 1 over n, I recognize that it's a series with alternative terms, and bn is going to be 1 over n. And if showing it's decreasing and the limit is 0, so if showing these two steps are straightforward, there's not a lot of work that you need to do to prove that the limit is 0 and that is decreasing. All I ask you basically in exams or quizzes is to just state the two conditions so that you show that you are aware of the two conditions to be verified. So for example, you can just say, I mean, I'll believe you that it's obvious in this case that obviously Bn 1 over n is decreasing. You could also show basically what you mean by Bn plus 1 less than Bn. There's nothing else that need to be said here, right? I mean, obviously, if I increase the denominator, I'm going to lower the fraction. So clearly 1 over n is decreasing. And for the second condition, just simply state that the limit of 1 over n is 0, because again, it's one of the basic limits we learned from calculus 1. 1 over infinity. 1 over infinity is 0. If either of the three is not obvious, you have to show more steps maybe, as I'll talk about on the next page. So stay tuned for a couple of more examples. All right, so let's do another example. Let's say I want to study the convergence of the summation from 1 to infinity of -1 to the n minus 1 of n over n squared plus 1. With a little bit of experience, you could tell from the beginning whether it is convergent or not in many, many cases. So for instance, I'm staring at this one. So I notice it's alternating. I'm staring at this one, which is your Bn, if you fit it with the generic way you writing it, right, or of an alternating series. And I notice it's going to be 0, right? So one of the conditions that the limit of Bn as n goes to infinity being 0, it's again clearly understood. Remember, I'm not going to ask you to go too far on this with the proof. If you like, you can look at the ratio of the leading coefficients, which is what you do to estimate limits like this when you have an infinity over infinity case. I don't want you to waste more time than this in cases like this. You don't have to do L'Hopital, or you don't have to divide by n. Infinity over infinity involving polynomials, everything boils down to a limit of just the dominating terms, and that tells you quickly what the limit is. So it's 0. Now, is it decreasing? Again, I can suspect it is, but let's say it's not that obvious as the previous case, because you have n on both sides of the fraction. So in that particular case, you may want to show that Bn plus 1 is indeed less than or equal to Bn. So we need to do some algebra. Bn plus 1, if I replace n with n plus 1, then you can move everything to one side and write the common denominator, or actually you can cross multiply. So basically you need to check, well, let's just do it via fraction, I guess. It's more, so we need to check that n plus 1 over, and let's expand the bottom, n squared plus 2n plus 1 plus another 1 minus n over n squared plus 1. We need to show that this is less than 0. Common denominator is the product of these. So we have n plus 1 times n squared plus 1 minus n times n squared plus 2n plus 2. N squared plus 2n plus 2 over n squared plus 1. We need to check this basically. So the numerator, if we expand it, n third plus n squared plus 1 minus n third minus 2n squared minus 2n. And let's see if this is less than 0. Well, we have some nice cancellations on the top. And if you look carefully here, when I have n squared minus 2n squared, that becomes minus n squared on the top. N minus 2n is going to be minus n plus 1 over some quantity that is positive. This is obviously less than 0. If you look carefully, that means, if you look at the top, minus n squared minus n plus 1 is obviously less than 0, because that's equivalent to n squared plus n greater than 1, which is true for n from 1, 2, 3, and so on. That's really enough in terms of the work here to show that the series is convergent. So, conclusion: by alternating series test, the original summation is convergent. Now, here comes the fun part. Make sure you don't confuse these concepts, okay? So again, let's put these two side by sides. Summation from 1 to infinity, 1 over n. That's not an alternating series. That's a p-series with p equal to 1, hence divergent. That's the p-series test. Summation from 1 to infinity minus 1 to the n minus 1, 1 over n. That's a completely different series. This is alternating. So by alternating series test, which we established before, 1 over n goes to 0, 1 over n decreasing, therefore the series is convergent. Always make sure whether the test is applicable before you jump and draw any conclusions. There is another neat thing about series with alternating terms, and this one here I'm going to just state it without proof, although I'm going to show you a quick example that I'll ask you to check on your own with the calculator. With alternating series, we can quickly estimate the exact sum of the series, which, remember, it's not an easy thing to do. It's quite difficult in general to figure out what that limit is if it's convergent. So you notice the best we could do most of the time is to say a series is convergent, but what is it equal to? Now, there are ways to do that in many cases, but in general, it's not a simple problem. For the alternating series, it turns out that you could always estimate the partial sum by simply looking at the value of the next term. So if you add n terms, so let me write down here the main concept. So estimating partial sums of an alternating series. So it turns out that the n plus 1th term in the series approximates the error of the difference between the exact sum and the partial sum made of the first n terms. I think I ended up writing a much longer sentence than I wanted. So so what I meant here, actually, let me make a small correction and I'm going to illustrate immediately. What I meant here is the estimating, cross this out, estimating the sum, the exact sum of an alternating series. So you don't know what that sum is. If it's convergent, how do you estimate it? So it turns out that the n plus 1th term in the series approximates the error of the difference between the exact sum and the partial sum made of the first n terms. So let's write formally what I mean by this. So if you have, let's say, an alternating series and suppose it is convergent, which means this is equal to some real number s, right? The limit of the partial sum. And in practice, of course, you don't know what this number is, but you could always add finitely many terms in the series. So let's look at the sum, the partial sum obtained by adding the first n terms in the series. b1 minus b2 plus dot 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 minus 1 to the n minus 1 bn. So it turns out that if you look at the difference between the exact sum and the sum obtained by the partial sum, right, adding in numbers, this difference is going to be actually less than or equal to bn plus 1. So the nth term, disregarding the minus or plus in the series, in the series, basically can be used to estimate the difference between the exact value and the value obtained by adding the first n terms. So this will tell you a quick way, and I'm going to show an example on the next page. This little result can tell you quickly how many terms you need to add to obtain a given error of approximation. Right? So if you want to approximate the exact sum by adding finite many terms, the more you add, of course, the better the approximation is. This way, this estimation can tell you quickly how many terms you need to add. So I'm going to illustrate this with an example on the next page. So stay tuned. All right, so let's suppose we have this example from before, right? This, well, I don't know if actually I did this before, but so an alternating series with Bn given by 1 over n squared. So again, it's going to be convergent, right? Easy to see by alternative series test that 1 over n squared is decreasing. 1 over n squared goes to 0. So it's convergent. And let's say we want to add enough terms so that the partial sum is within, let's say 0.01 of the exact value of the series, the exact sum. So in other words, the question is how many terms do we need to add to be within 0.01. So basically what you want is to add 1. So the first one is actually 1 over, let's write it down like that. So the first one is 1 over 1 squared, the next one is minus 1 over 2 squared, then plus 1 over 3 squared, and then so on. We want this, basically this summation, all together. If you take the difference between that and the exact value, whatever that may be, right, you want this to be less than 0.01. Let's say less than or equal to 0.01. Now, the result that we mentioned before states that, again, this Sn, right, the nth partial sum minus the exact value of the series actually is always less than Bn plus 1, the n plus 1 term in the sequence, which in my case is going to be 1 over n plus 1 squared. So if I add enough terms so that Bn plus 1 actually is less than my desired error, then that number basically ensures that the partial sum is within 0.01 of the exact value. So all you have to do is to take the n plus 1 term and make it less than your desired error, essentially, which is 0.01, and that'll tell you, if you solve that inequality, it will tell you how many terms you need to add to be within that error. So let's see if we solve this inequality, 1 over n plus 1 squared less than or equal to 0.01, which is 1 over 100. If we flip this, that reverses the inequality. So that's n plus 1 squared greater than or equal to 100. If I take the radical, that means n plus 1 greater than 10, which means n greater than 9. So that means we need to add at least 9 terms to be within that margin of error. So now take your time to do it with your calculator. I did this ahead of time, but if you do the summation from 1 to 9 of minus 1 to the n minus 1 over n squared, you should end up with 0.8 27962. 8.27962. If you do a little bit more than that, because again, it's at least 9 terms. The more the merrier, basically. So if, let's say you do 10, from 1 to 10, minus 1 to the n minus 1 over n squared, that'll be even better. It's going to be 0.8179. And again, this will be basically hovering around the exact limit, because remember, this is an alternating series. You keep on adding and subtracting something. So your approximation will be either above or below the exact limit, but very close to it, within this margin of error. If you plug in, let's say, Wolfram alpha, the full series from 1 to infinity of minus 1 to the n minus 1 over n squared, you will get 0.82247. Actually, the exact value is going to be pi squared over 12. How that's the case, how you prove that to be, it's beyond what we do here. You can do that with Fourier series, for example. But this is just to give you an idea of how close these approximations are to the exact value of the series, of the summation. So I think that's it for today. I think, yeah, so the next topic will be yet another way to check for convergence. And then after that, we're going to review some stuff related to the convergence, and we're going to finish this unit with applications of series, in particular power series and other interesting stuff to end with. So that's it for today.